Hello everyone. So today we're going to cover chapter 1 of our book. This is lesson 1 for Chem 1411. Okay, so chapter 1 is about science and measurement. This is really a review of concepts that you should have learned in high school. So I'm going to go kind of quick. I highly recommend you to have your calculator handy because we're going to do some calculations and I would love you to do them with me. Okay? So this is today's agenda. We're going to see the classification of matter, properties of matter, matter and energy. We're going to give a very quick review of the scientific method. And most importantly, we're going to see the international system of units and how to do some dimensional analysis. Okay? So let's start. Classification of matter. But first we have to define what matter is, right? So matter is anything that has mass and occupies a space. Anything with mass that occupies a space. That means that matter will be formed by atoms, right? But what are atoms? So atoms are the smallest particles of any element, but that they still have the characteristic of that element, right? So atoms of calcium are going to look exactly the same. Atoms of sodium are going to look exactly the same, etc. Okay? Now, matter, we can divide it into two categories. One is a pure substance and the other one is a mixture, okay? Now, a pure substance is that matter that is either an element or a compound. What is the difference? Well, the difference is that in an element, we have molecules formed by the same type of atoms, okay? So this could be, for example, gold, could be silver, could be iron, right? As long as they have exactly the same type of atoms, then we call it an element. And these atoms are bonded in some specific way, right? Now, if we bond different types of atoms, like in this case, right, we are going to call it a compound. Okay, now the particular characteristic of a compound is that these atoms are always the same. For a specific compound, they are always the same, and they are always combined in the same proportion. Okay, so for example, if I have an atom of, I don't know, sulfuric acid, let's say sulfuric acid. To call it sulfuric acid, we are gonna have always two atoms of hydrogen, one atom of sulfur, four atoms of oxygen. And this is the only way we can call it sulfuric acid, right? If for some reason we have less oxygen, let's say something like this, then that is a different type of acid, that is sulfurous acid, and it is different because it contains only three, right? Now, once again, in this type of molecules, we have two or more different atoms combined exactly in the same proportion, okay? Now, the other category, sorry, is a mixture, right? So mixtures can be divided into heterogeneous and homogeneous, right? Now, what is that? What is an heterogeneous mixture and what's an homogeneous mixture? Well, an heterogeneous mixture is that one that is composed by two or more substances, and they could be elements or they could be compounds, but the characteristic is that they are not uniformly mixed. So this is, for example, mud. In mud, you have water, you have soil, but you can somehow distinguish the boundaries, right? Where the water starts and the soil stops, or vice versa, right? Now, we have also homogeneous mixtures, and these are mixtures, again, composed by two or more substances. And once again, they could be elements or they could be compounds. But the main characteristic is that they are uniformly mixed, so we cannot tell when one starts and the other one ends. All right. Now, we usually call these mixtures solutions, okay? Because we cannot distinguish any boundaries, like in this drawing here, right? Now, there are different types of solutions, even if the most common is the solution of solid in water or solid into a liquid, like a lemonade or like sugar in water, etc. There are many types of solution. Those are not the only ones. For example, we have here a solution of solid in solid, and it's, for example, brass or bronze or you name it. So these are two solids that were melted, and when they were in liquid state, they were combined, and then they would lead to solidify. And in this brass, for example, you cannot tell where the zinc ends and the copper starts. Okay. Now the next one is the most common, solid in liquid, and the example is sugar in water or salt in water or you name it. We have also solutions of liquids in solids, and this is, for example, a solution of mercury in silver. Mercury is the only liquid metal that we have in this world, okay? These were used long time ago in your teeth, just to cover the cavities. I still have some, because I'm from that age, right? Now, the use of mercury is forbidden because it's kind of toxic, although I'm still here. I'm not dumb. I'm not. Anyway. But yeah, mercury is kind of toxic, so it was forbidden a few years ago. The next type of solution is, for example, liquid in liquid. And the example is gasoline. Gasoline is a mix of hydrocarbons, and we have here octane, heptane mainly, but we also have some ethanol. We also have some hexane. So these are many, a vast variety of liquids mixed into something that we call gasoline, okay? Now, the next type of solution is gas in solid, like for example, hydrogen in platinum, right? And this is a catalyst. Or this one is very typical, gas in a liquid. Every soft drink that is carbonated has CO2 and water, and CO2 is in the form of carbonic acid, okay? And the last one is, for example, gas in gas. So air is an homogeneous mixture. It's a solution, and it contains mainly oxygen and nitrogen, although it contains also a very small amount of argon, some CO2, depending on where are you at. Some cities have more CO2 than others, right? But I bet you cannot tell in the air, oh, this is oxygen and this is nitrogen. You can't, right? Because it's a solution, right? So we have here examples of these elements, compounds, and mixtures. So in the first squares here, we have elements, and elements, if you see, they can be formed by only one atom, right, like gold, or they can be formed by two atoms. And we call these molecules diatomic. Let me write it here, just in case my pronunciation is not the best. Hold on. We're going to put it here. These are called diatomic molecules, right? And we have 7 types of diatomic molecules, only 7. Those are hydrogen, oxygen, nitrogen, fluor, chlorine, bromine, and iodine. Okay, these are the only types of molecules that can be diatomic. Okay. Now, we also, in this second column here, we have compounds. And if you see, this is, I guess this is water or something with two little atoms and a big atom. Okay. And they can have a proportion of 2 in 1, or a proportion of 1 to 1, or even 3 to 1. Doesn't matter. But remember, the main characteristic of the compounds is that the proportion is always the same. The composition is always the same. Okay. And over here we have different types of mixtures. Okay. And the mixtures can be atoms, right? Like in that bronze or brass, solid into solid. They could be some atoms mixed with some compounds, right? Or they could be a mix of compounds. All of these are mixtures. And it depends. If we can distinguish the boundaries, then that is going to be a heterogeneous mixture. And if we cannot distinguish the boundary, that would be a homogeneous mixture. All right? Okay, let's move on now. So let's talk about properties of matter. But let's define first what is a property. So a property is a characteristic, but again, it is a characteristic by which something can be identified, right? So a property of you could be black hair, red skin, if you went to Galveston this weekend, or long nails, or you name it, big feet, small feet. That's a property of you, right? Something that we can use to identify the matter. In this case, it was you, right? Now, we're going to divide the properties into physical and chemical. Physical properties are the ways that a substance can be described or identified. The most important part is coming, without changing its chemical composition. Okay? So if we can identify something without changing the chemical composition, then we call it physical property. And in general terms, a physical property is that we can either see, hear, feel, measure, smell, or touch, right? So something that we can observe with our senses, right? That's gonna be a physical property. So for example, this gold shiny, something we can see, or this metal producing some sound, or the consistency of the rubber bands, or if something is hard or soft. So shine, ability to produce sound, the rubbery or soft or hard, or the smell, or a characteristic that we can, for example, the characteristic that we can measure. For example, we can measure the temperature, but we can also feel the temperature, right? We can feel if something is hot or cold, right? All of these are physical properties. Now, chemical properties are those properties that we are going to use to identify a matter, but to identify that property, or to not see that property, the substance has to chemically react with another substance. And that means it has to change the composition or the initial identity. So for example, toxicity. Okay, so if you drink too much of an acid, for example, that acid is going to react in your stomach and is going to produce some other substances, right? That those substances are going to cause some effect in your organism. So we said that that substance is toxic, right? Also the oxidation states, and we're going to cover this later in the course. The heat of combustion also we are going to cover it later, but this is the heat that is produced when something is burned in general terms. The chemical stability, how easy a reactant is gonna react, right? There are some compounds that are hard to react and we have to either apply some heat or add a catalyst, right? And there are some others that react immediately, right? The flammability, and this is also a reaction, and we call it combustion reaction. So how easy is for something to get into flames? For example, alcohol. Alcohol is very flammable. If you put alcohol very close to a flame, I bet you're going to have a fire, right? But if you put, I don't know, a rock into flames, well, they are probably going to increase the temperature, but they are not going to produce flames, right? They are not going to produce fire. So flammability is also a way to describe chemically a substance. The coordination number, we're going to cover this in 1412. Once again, the reactivity, and this is related to the chemical stability. Is that substance something that is going to become another substance easily or not? Okay. The possible chemical bonds that are formed. Also, we are going to cover the part of chemical bonds later in this course, or the enthalpy of formation. And we're going to cover this. This is related to the heat of reaction. Okay, so all of these are chemical properties, and you can add here corrosion, the degree of explosion that some substance can produce, etc. Okay, now having said that, let's move on to physical and chemical changes. And this is pretty much the same definition. So a physical change is that change in which matter will form, but the identity of that matter is going to be preserved. So for example, we have here ice that is melting. So initially this was solid water, and at the end it's just liquid water, but the identity of that water is preserved, okay? So really any change in the state of matter is a physical change. You name it, evaporation, sublimation, condensation, all of them are physical changes because the identity is preserved. Now, if you reduce something to smaller pieces, that's also a physical change because each one of these smaller pieces are going to preserve the initial identity or the identity of the substance, right? Once again, you are reducing the size of something here, right? Or if you just mix and that mix creates an heterogeneous mixture, like mixing gray and green marbles, right? All of these are physical changes. Now, the difference with the chemical changes is that after a chemical change, the identity of the initial substance changes. And it says here, new products are formed. So for example, if you burn something, I bet you have seen this, instead of wood, you are going to have ashes, right? So new products are formed, and therefore this is a chemical change. When something is roasted, the final product here is different than the initial product. I'm pretty sure you are not going to eat a banana full ice, right? Why? Because it's not a banana anymore. It's something different in composition that is called rotten banana, right? Now, if you mix vinegar and baking soda, you're gonna see this nice foam being formed, and that means the composition of the vinegar and the baking soda changed because there was a reaction here, right? Same happens with fireworks, okay? I hope this is clear, guys. Moving on. So we have matter and energy. And this is just a very quick review about these two concepts. So we said that matter is anything that occupies space, right? And is formed by atoms. Now we can also distinguish this matter as mass and as weight. So the mass of that matter is just how much, what is the amount of that? So how many atoms are present there, right? And this one is usually, well, it's not usually, it's measuring units like grams, like pounds, like kilograms, etc., etc. Okay? Now, a different unit is weight. Okay? Now, weight is, and I'm going to put it here, weight is nothing but the product of the, hold on, what is my pen? There. The mass times the gravity. Okay? So this is the mass that we have here, but to represent it as weight, we have to multiply it by the gravity. Okay? So the units are different here. I'm not going to tell you the units now, but just make sure that you know the units are different. And since weight depends on the gravity, this weight is gonna depend on where you are, right? So if you are in planet Earth, the gravity is more or less 10 meters over a square second. But if you move to the moon, the gravity is around, let's put it here, 1 meter of square second. So your weight is gonna be way lower, 10 times lower in the moon. I'm about to move to the moon. So because my weight is lower there, right? And if you have no gravity, you have no weight, okay? Even if you have a mass, if there is gravity, there is no weight, okay? Now let's talk a little bit about energy. And this is the simplest definition that you can find. Energy is the capacity to do work, all right? Just like that. All right. Now we have different forms of energy. For example, electrical. Heat is also a type of energy. I bet you remember the potential energy, and this potential energy, if you remember from your high school classes, this potential energy is the mass of an object times the gravity, means the weight, but times the height. So this potential energy depends on how high my object is located, and this is energy that is stored, right? Now we have also chemical energy, right? We are going to have atomic energy, and we have, for example, kinetic energy. So kinetic energy, if you remember, is, let me see, kinetic energy is 1/2 of the mass times the speed square, or the velocity square, right? So potential energy is due to the altitude or the height, and kinetic energy is due to the speed. Now, we can convert from one type of energy to another. The thing that we cannot do is to generate energy out of nothing, or to consume energy and disappear it totally, right? That's what we call the law of conservation of energy, where energy cannot be generated, cannot be, cannot disappear. It is only transformed. And one example of that is, let's say you have a bulb, right? So you have electrical energy flowing through that bulb and producing some light. But if you put your hand and touch that electrical bulb after an hour, you're going to see that there is some heat there. You're going to burn your hand. That means this electrical energy was transformed into heat, right? Or energy in the form of heat. Now, for example, if you burn something, this is chemical energy being released, right? But it also might produce or might consume heat. So we are transforming chemical energy to heat if the heat was released, or we can add heat to convert it into chemical energy if the heat was consumed, right? Same with the potential and the kinetic energy. If you are on the top of this roller coaster and if you are stopped right here, you have a huge amount of potential energy. But as soon as you start moving and start gaining speed, that potential energy is going to slowly or quickly, I don't know, depending on the roller coaster, but it's going to transform into kinetic energy to a point that you have no height and all that potential energy was transformed into kinetic energy, right? I hope you remember these because these are very easy concepts that are actually even in middle school you will cover these concepts, right? Now let's move on to the scientific method. And to explain this a little bit better, I'm gonna use a very easy example. So let's see this example here. Let's say I have my little plant that is kind of small and probably the leaves are brown and probably the smell is not what I wanted. There are some nice flowers that smell really good, or probably it's because it doesn't have flowers. Anyway, whatever we can see, like the color or like the size, things that we can measure like the size, or things that we can feel like brittle leaves, that's an observation. So I'm going to make an observation first. And based on that observation, in this case, I decided that my plant needs some fertilizer. But then I asked myself, which type of fertilizer works the best for this plant? Because not all of them work exactly the same with every single plant, right? Probably you know this better than me, right? So I go to the store and ask which one is the best fertilizer for my plant, and they recommend me several brands, but they say plant fertilizer A is going to be the best for your plant. Anyway, I don't trust them. So I buy the three of them, but with the idea that fertilizer A is going to be the best for my plant, right? So that's my hypothesis. I'm saying this one is the best, okay? So I go home, buy three plants, exactly the same type of plant, and I start my experimentation part, okay? So I apply fertilizer A to one of the plants, fertilizer B to the other plant, fertilizer C to the other plant. I come back in a regular basis and I probably add the same amount of water, they receive the same amount of sun, so those variables are constant, right? The only thing that is gonna change is the type of fertilizer. I also add exactly the same amount of fertilizer, so that is constant. And I take notes in my diary. I measure again my plant. I see the color of the leaves. I touch if my leaves are brittle, and all of those are results. And after a period of time, I can have probably a table with different results that I took all this time. So now, based on my results, I can generate a conclusion and say, yeah, fertilizer A was the best, okay? So my conclusion in this case is the hypothesis was proven correct, okay? So this is really these are the steps of the scientific method. So let's see it now in a more formal way. And this is really what you're going to do in your lab, all these course, in your experiments. So first, you are going to observe something, right? And based on that observation, you are going to come up with a question. And you are going to try to answer that question. And that's your hypothesis. So initially, you have an answer to that question. This is what is going to happen, okay? And then you go and do your experimentation, and you can have one of these two results. Your experiment can go perfectly right and prove that the hypothesis was correct, right? And then you have evidence that supports the hypothesis, right? And you can probably do more experiments so you can support even better. You can tell to your colleagues about your experimentation, and they can do the same experiments. And if everyone agrees, then you have a scientific theory, right? However, your experiment or the result of your experiment can contradict your hypothesis. And this is not a bad result. This is not, once again, a bad result. It's just you cannot formulate a theory. Or you can say in some way, this hypothesis does not fulfill my expectations. And that's some sort of result, right? So you will change your hypothesis based on what you got in your experiments and start the process again. And you will probably stay in this cycle until your hypothesis is correct, because it agrees with your experiments, and because other people are getting the same result as you, and then you formulate a scientific theory. Okay? Now, when we talk about experiments, this part here, there are two aspects that have to be fulfilled. Okay? So for your experiment to be good and in a way that you can move on, you have to fulfill these two things. Your results have to be precise, and they have to be accurate too. So precision is when all your results are exactly the same or very close, right? Even if they are different than your goal or your target, if you have those results looking exactly the same, or as I say, are very closely the same, then your results are precise. Something different is accuracy. Accuracy, it refers to if that measurement agrees with the correct true value, or if that value is hitting the target, right? Or fulfills your goal, okay? So for example, here, we have something that is very precise, because all of them are in the same place, but they are not accurate because that would be your target, no? In this case, well, the results are not exactly precise because they are all over the place, but they are kind of accurate, right? It depends how, if you define your accuracy as being on the third circle here, right? So, well, this is kind of accurate, but it's not precise. In this case, they are neither accurate nor precise because they are all over the place, and only one is in your or close to your target, right? And in this case, all of them are in the same place, which is the target, so they are precise and accurate. So once again, these experiments to be accepted, they have to be precise. In other words, they have to be reproducible, and they have to be accurate. So they have to confirm your hypothesis. This is your goal, right? If they are precise and accurate, then you can move on this way. If any of these If they are not precise, you have to do more experimentation. If they are not accurate, then you have to do the cycle again. Okay? Now, let's move on to what we call uncertainty. Because when we talk about accuracy here, let's take this example. We said that, well, if they are not exactly in the center, but we take it as accurate because there was an error that was assumed to be correct or that was assumed to be accepted. And let me explain a little bit more about that. And that's where we have to define uncertainty. So it says here, all measurements have some degree of uncertainty based on the limitations of the measuring device. So accuracy is not always, it doesn't always mean all in the center. It means all in a range, within a range, because you are limited according to whatever you are used, equipment you are used to measure your result or your experimental data, right? And this one applies a lot in the experimental data you are gonna do in your lab, right? Because there are some devices that are more accurate or more precise than others, okay? So it says here in chemistry, the standard is to record all the certain digits redirected from the scale and one uncertain digit. So we're by guessing one or estimating, that's a better word, one more digit, we are trying to decrease the degree of uncertainty. And let me explain this a little bit better. If we measure volume, these are two devices that are very commonly used in the lab. So this one here is what we call, let me see, hold on. This one here is what we call the graduated cylinder. And as you see, we have different sizes of that graduated cylinder. And over here we have that we call the burette, right? So there are some difference between the graduated cylinders and the burette. Both of them are used to measure volume, but you have, for example, the 5 milliliter, or no, this is 10 milliliter, 25 milliliter, 50, no, this is 50, this is 100, different sizes. So according to what volume you can measure or the capacity of these graduated cylinders, you're gonna have a scale. They are gonna be divided into a scale. So I believe this one is the 100 milliliters. So the scale goes every 10 units or every 10 milliliters, okay? Let's say, for example, the level of my liquid is right here. And by the way, we have to measure of the liquid in the lowest part of the menisc, okay? So that line there represents the lowest part of the menisc. Now, if we read in this scale, we can see that between 30 and 40, we have 10 milliliters, right? That means that each one of these 10 small lines represents 1 milliliter, right? So with 31, 32, 33, 34, 35, and that's a kind of bigger one. 36, 37, 38, 39, and 40, okay? So in this case, my line is at 35, 36, 37, 38 point, let's say 5. I don't know what you guys think about it, but let's say this is 38.5 milliliters. So if you see, the scale gave me this 38. But I still had to guess this 0.5, okay? That's what the previous sentence said, we have to guess or estimate one more digit in order for the results to be more accurate, okay? And that is fine. If you think that is 38.4, you're still correct. If you think it is 38.3, you're still correct. It doesn't matter. We are still increasing the level of accuracy, decreasing the uncertainty, okay? Now let's take this instrument right here. In this instrument, now if you see there are several differences, right? Even if this is a 50 milliliters puree, I think so. First, the scale is not in this other case, in the graduated cylinder, the scale was every 10 milliliters, right? Now in the burette, the scale is every milliliter. Okay, it goes from 38 to 39. So we are decreasing the uncertainty by increasing the divisions here, right? Now, the other thing is a graduated cylinder is read from the bottom to the top, or the scale goes from the bottom to the top. So it's 0, 10, 20, 30. And in the burette, the scale is the opposite. It starts in 0 at the top, and then it goes 1, 2, 3, 4, 5, until probably 50 or whatever the capacity of your burette is, okay? So in this case, we have 38 here, and we have 39 here. Look at the difference, because now every single line here is 0.1, right? 38.1, 0.2, 0.3. So I have here 38.1, 2, 3, 4. 38. Let me put it right here. This would be 38.4. But then we have to guess one more digit. So that will be probably 0.4. Let me see. 1, 2, 3, 4. No, it's 38.5. Sorry. Let's see. Let's fix that. So 38.5, and then if I guess one more, let's say 0.54. All right. So if you see this 38.5 was given by the divisions, and I guess one more. But by giving one more decimal, I'm decreasing even more the degree of uncertainty. I'm making or trying to produce more accurate results. Now, this wasn't a human error, because it is not something that depends on me or in my ability of reading the level. That was due to the limitations of the equipment. So a graduated cylinder produces more uncertainty than the burette. And I really wanted to explain this, because when you do your results, the discussion of your results or your conclusions in your report, usually people tend to blame on human errors. If you don't have a good result, they blame on human errors, like I probably didn't check the weight of my or the mass of my object correctly. That's human error, right? That's your fault. Or I probably didn't read the volume correctly. That's your error, right? That's human error. Or my partner did this wrong. That's human error again. Or this type of errors. The scale wasn't balanced. They are, right? I'm in charge of that. So we cannot blame those type of errors, which are human or machine errors, right? In order to explain why our results don't agree with the theory or with the hypothesis, right? We have to use errors that do not depend on us, like this one here. But how precise is my equipment? Well, if the measurement was made with a grounded cylinder, we already know that it was probably not very precise, but because of the equipment, not because of you, right? So let's move on. Sometimes precision or accuracy, it could be a little bit like a loose concept. It depends what kind of measurements or what is the purpose of my measurement. So for example, if I want to measure the temperature outside my house or the temperature of my house, I am fine with integers. So in this case, we have 20, 22, 24. And if you want to be more accurate, let's say 24.3 degrees. But really, if you are looking at the weather, 24 or 24.3 are the same thing. We don't care, really. But if we are measuring your corporal temperature or your body temperature to see if you have a fever, then yeah, 98.6 is not the same as 99, right? One might be considered fever and the other one is okay. So in this case, we need a device that produces more decimals or a device that is more precise, more accurate. So it also depends on what is our goal. Okay? All right, I'm gonna make a pause here. You guys can stop, stretch, and relax for 5 minutes and then continue with part B of this class. I'll see you soon.